So today we're going to talk about spatial statistics. And so we have like 3 topics left. And I put this together last year since I think it was kind of appropriate, getting in towards Thanksgiving. I'm not sure if you guys are planning on eating a lot this week or not. I don't know if you like food. I like food. I'm fairly thin, but I eat a lot because I run. That's one of the benefits of running is you can enjoy some food and then you can run it off and stuff like that. So what I am going to do with the topics, and I think I mentioned this before, sometimes food is a nice way to remember stuff. So we have 3 topics I'm going to talk about today and Wednesday, including spatial statistics, measurement error methods, and causal modeling. Okay, I think there's actually a class in causal modeling that we have that FAM teaches, and so this is just one little piece of causal inference that I'm going to talk about, and that'll be on Wednesday. But that's marginal structural models, which is kind of interesting and does apply to the longitudinal modeling. We'll get into how that ties together. So today, in this slide set, I made this last year, and I tried to pack it into one day, and it's kind of a lot for one day. So I'm going to take 2 days to go through this material. And today I wanted to actually start on, I'm going to jump to the spatial statistics, because I felt like this is a topic that might actually relate to more of you and what you're doing for your project. And I know that there's 2 people that are doing topics in spatial temporal modeling and probably have already kind of worked ahead in that. And then Laurel is actually maybe considering that for a master's topic. So it seems like to me, spatial temporal modeling is becoming more popular because we have more data that's conducive to this. So we have, longitudinal data is common and has been around, and data collection. I mean, data is being collected more and more. More big data, more data are available because we have the technology to collect it, and so the methods are now trying to catch up with the data, the data that's available so that we can analyze it. So spatial statistics applies to data collected, over space. And I would say in most cases, it's data collected really over area. I mean, it's space, but if you consider data collected in Colorado, then it's spatial data, but you can easily consider that 2-dimensional, right? Because there's not that much curvature to, a state because it doesn't cover that much of the Earth. So you can typically get by modeling spatial data in 2 dimensions rather than 3. Now, Jonathan's actually working on, I need to talk to him more about what he's been doing recently, but he actually has world data where he's looking at climate data and things like that. And so at that point, obviously 2 dimensions isn't going to work anymore if you have data, considering data collected around the world. But that's the question is, how much area does it cover, the spatial data that you have? And can you simplify it to 2 dimensions as an approximation to the spatial data that you have? If you do, then you have 2 dimensions that you have to work with. And then if you have the temporal piece of it, then you have really 3 dimensions that you're working with, 2 for space and 1 for time. So the thing about spatial temporal data is you may be interested in one of those more than the other. You may consider it spatial data, but you just have it collected over time and you want to account for that correlation over time. Or you might consider it as temporal data, and the spatial component is the nuisance factor. Okay, or you may really be interested in both. You may be interested in the spatial and the temporal jointly. So depending on what you're interested in will dictate the specific methods that you would use for that. There are a lot of different spatial methods, and then when you get into spatial temporal methods, there's just really a lot of methods that have been developed over the last 10 years or more. From what I can tell, it seems like R has more available right now than SAS. There's a few, there's some spatial methods in SAS, some procedures. There's not a lot of spatial temporal modeling choices that you have in SAS, but there seem to be more in R actually. So I would say R has the upper hand right now for methods for spatial temporal data. If it's just spatial data, then it may be more equal. So we're going to talk about kriging as the specific type of spatial method, and we're just going to really consider spatial modeling today in what I'm going to present. So again, you know, longitudinal data, the spatial data, it's correlated data. So in my mind, that still really applies to this class because this class is really about correlated data. If you want to get into the longitudinal component, then you're talking about spatial temporal data analysis. So spatial statistics gives us methods to conduct inference for data collected in space, where dependence between observations in space is typically higher for points closer together. So it's the same issue, like for longitudinal modeling, we typically see that for two outcomes that were measured closer in time, we expect those to be more correlated. And then as you spread the time up further apart, they typically are less correlated. And if you use a structure like the AR1, the first order autoregressive, that will naturally account for that. It's the same issue for spatial data, where we typically are going to assume that the closer in space 2 points are, the more correlated they're going to be. And as you move further apart, they're going to be less correlated. So why do we need to worry about it? The main reason is because we're going to get more accurate inference. Even if our interest is not in that correlation, it's maybe we're more interested in the fixed effects themselves that may be describing something else. But we are more interested in that. But even then, to get the best inference, to get the best estimates and the best standard errors, we need to account for the correlation of the data in space as well as time, if that applies. Okay, so what's really cool about what we're going to talk about today is it's very related to what we already know. Okay, we've talked a lot about linear mixed models and predicted values and estimates and things of that sort. So what we're going to talk about today is actually not veering off too far away from what we have already talked about. So bloops, you guys know what that is, what a bloop is? So if you've had theory, you're probably familiar with this, this term. What does that stand for? See if it's on the tip of your tongue here or not. Anyone from theory?
Is it best linear and best predictors, or?
That is right, Benjamin. So this is best linearly unbiased predictor. And that applies to predicted values that include both the fixed effects and the random effects. So we're going to predict y hat, and you can see this is essentially the linear mixed model, except for the error piece, right? We don't need that because we're getting the predicted values. When you get the predicted values, then you're not worried about adding the error there. And we put the hats on. Those are the estimates of the fixed effects, beta, and the estimates of the random effects. And so these are the predicted values we get from our linear mixed model. And the form, based on maximum likelihood estimation or REML, you can use those to get your beta hat. And then we use the empirical Bayes methods, right, to get the estimates of the random effects. And if the data are all observed, then our y hat are the best linearly unbiased predictors. Whereas for the fixed effects, those are the estimates we have for those are best linearly unbiased estimators, BLUE or blue. But here we're talking about the predictors that include both the fixed effects and the random effect estimates. Fixed effect estimates, random effect estimates. But the thing is, if we have missing observations, then how do we get those bloop estimates or predictors? It has this form that I'm showing you. I'm not going to get into the derivation of it, but this is the form of predicted values when you don't have the observed value for y. Okay, and so you can show that this form that I've circled here, that's the form of the bloop estimator when the corresponding y is not observed in that case. Okay. The thing that's nice is that SAS, if those are missing, the predicted values are going to be automatically generated. So you have your data set, you have your x variables, your y variables, and if y is missing, you put in that dot, right, for the missing value. When you get your predicted values using the outp option in the output statement, then you automatically will get those predicted values. Okay, so it's very easy to get these predicted values for when the y is not observed. And the thing that I want to mention too is that maybe I can write this down below. So we can take our y vector and we can split that into, so our complete y, we can split that into y observed and y missing and make a vector out of that. So we can sort it so that we have the observed values and the missing values. And then the corresponding X and R are going to relate to that sort. So we have our R matrix. I'm just going to jump to R. You can split that into okay. So we can split that into 4 pieces. R observed, are missing. And then let's see. It's going to be the correlation between the observed and the missing values. It's really messing with me today. I'll go up here. And one is going to be flipped from the other. I'm trying to remember which is which. I can modify this, but the main point is that the correlation between the missing and observed is going to be okay. So we're basically taking our R matrix and we're considering the R elements that are associated with the observed Y and those that are observed, those that are related to the missing Y. And we're sorting the R matrix in the same fashion. So, and you can do the same for X. Okay, wish me luck on this one. Ready? If I do it really slow. No. Really fast. Okay, I found the tool. You do it really fast, it works. So does that make sense? Any questions on that? That I'm just trying to describe what these the missing and the observed elements of the data are and how they relate to it. In this case, it's all based on the observed or missing Y. So X sub m would be the X that's related to the missing Y components, right? And the same for R. R sub m is going to be the R as it corresponds to the missing Y. And R sub O is going to be the R that relates to the observed Y, and so forth. I do it really fast. Let's see. Really fast. Then I don't write as well. So I'm probably what I'm gonna do is I'll post this and did I have MO, OM? I don't remember the order, but it's just the covariance between the observed and the missing is the main point there. So I think, what did I write here before? Was it OM or MO? Does anybody remember that?
You had OM.
Okay, so I think I'm gonna just to be consistent with what I wrote before, I might change that if that's not the right order of those two, but I'll let you know. I'll post that. So what we can do, why are we worried about missing and observed with spatial data? Well, what you get in spatial data is you're going to get observed points in space, but you're not necessarily just interested in those points. You want to know what are the estimates, throughout the whole area and not just for those points. And so what we do is we create a grid over the space for points that we did not observe. But we can treat those as missing values and then use the formula above here to predict in space what the average is going to be. So you collect data, where you get your data, you collect those points, And then you can actually make a surface, a mean response surface using this principle where we're just using our best linearly unbiased predictors, considering these as missing values. They're not really missing values, but it's really more like interpolation. We're interpolating estimates based on the data that we have around it. Okay, so the way you do that in SAS is you give it the observed Y, and then you can make extra records on a grid and essentially treat these as missing values, but then you get these predicted values for those extra points is what's happening. So the RMO, it contains the covariances between missing and observed responses. And it relies on the assumed covariance structure of the model. So if we put in like a AR1 type of structure, but in space, then that's a common structure that we would assume. When the correlation between missing or new is really a better use of the term, I think, for what we have. So when the correlation between the missing and observed, or the new and observed Y, is negligible, very small, based on the assumed structure, then the estimate is going to default back to the overall average. Okay, so the type of estimates we have for Y hat missing is we can consider these empirical Bayes estimates where we're gonna average two types of information: the population mean and more localized information that we have. And the stronger the localized information is, the less variable it is, and the closer you are to that, the more it's going to be weighted towards that. Whereas if you have less localized information, you default back to the overall average you have for the entire area. Okay, so they're very intuitive estimates, and I'm going to show you an example here in a second. We're going to see some examples of where the smoothness comes into play. We've talked about for non-parametric methods and for metrics like time and space. You're interested in smoothing out the estimates to get an intuitive surface. You want it somewhat smooth, but not too smooth. So in this case, the correlation structure is going to indicate how smooth the surface should be. Okay. I'm going to get back to that formula that I showed you, and we can talk about it more specifically. But I think right now, what would be better is to actually look at the data set to give you kind of an intuitive feel of how this works. So this is ozone data. Ozone air pollution. So we're not talking about the ozone layer, that's important for the human race to survive. But this is ozone pollution. Okay, so there's good ozone and bad ozone. The good ozone is the ozone layer that protects us from ultraviolet rays, and that's higher up. Ozone pollution is not so good because it can harm the lungs, especially for people that that are more vulnerable. And ozone really historically hasn't been an issue until the last, I don't know, maybe 10 or 20 years in Colorado. And it's more of a problem in the summertime when the temperatures are higher. So this data I got through Jim Crooks, who's my colleague here, and he got it through the EPA. So we have data, and just to show you where the data collection points are, I'm going to jump ahead here. So this is the state of Colorado, and these are the data collection points. And so you can see it's not on a grid. We just have different monitors available a lot of them are along the Front Range. So this is Denver, you know, just to give you a reference here, as you might expect. I'm guessing this is Fort Collins up here, and this is the western slope over here. So it's not ideal because we actually don't have any monitors in the southeast area where we have Lamar and La Junta, and we don't even have right here would be Pueblo. We don't even have monitors there. So this is not ideal, but it kind of helps to show how the methods work. Okay, so this is where the monitors are. And that's where we have our observed Y. So in our data set, we have the sites, we have the ozone level, and there's going to be dates as well. But in this case, I'm focused on individual dates so I'm focused on the spatial modeling. Okay, we could add the temporal component and do a spatial temporal analysis, but for now, keeping it simple, just considering the spatial data. So we have one fixed date here, and we have specific latitudes and longitudes for each site, okay, that correspond to that scatter plot of the state I showed you. And then we add in a bunch of extra points, and essentially, so these points here are on a grid. So these are the points on a grid where there were no monitors. Okay, and so we have dots for the ozone levels there. We didn't observe it there, but that's where we want to get the estimates. It looks like actually the data is open source, so I mean it's something that could be, you know, anybody could get. So here's the basic code. As you can see, it's pretty simple. You know, it's not really complicated, and it's just one step from what we already know. So we have our model, we have our ozone level. That's the response variable. I don't have anything there. What does that mean? That means we just have our fixed effects is just one intercept, right? We're going to get the intercept if we don't say anything. And so for our fixed effects, we just have an intercept value. So this is a very special, simple type of kriging that we're doing here. And we get our predicted values, then they're going to come into play based on adding this repeated statement. And we have a spatial power correlation structure for space. And we have the two components for that, longitude and latitude. So really pretty simple code that we use to get the predicted ozone temperatures at those grid points. And so by including this, the outp, this is going to produce the ym hat. So these are the estimated ozone at points on grid. Okay. So for the data that we have here, this is just a description of the dimensions of the data set that we have. And we're going to estimate, you know, we have a residual variance, and we have that correlation parameter in the spatial structure. And Dij is the Euclidean distance between two latitude and longitude pairs. corresponding to the two records being considered. And of course, this is how we get our predicted values based on the bloop estimator for the missing y, the y that we did not observe. We still get predicted values at those points. And just some dimensions of the matrix components that we have there. Okay. So I'm going to jump to the map that shows you the predicted values. And we have 2 time points. I fit a model for August 16th, 2016. And this is a view from the southeast. So as if you're in Texas and you're looking towards Colorado. And you can see what happens where we don't have data points. So around here, this was the southeast corner of Colorado, and we didn't have monitors there, right? And we didn't even have monitors near there. So the estimates that we're going to get are just the overall mean. So the flat, this whole flat area here, and here, these are going to be more based on the overall average. So that was the intercept. And then these values here are more based on localized data. And that's where we had the instruments, right? In Denver, Fort Collins, and so forth. And what we see is that we have high spikes in the Denver area. That's where the ozone is higher. There's more sources that emit the ozone along the Front Range and between Denver and Fort Collins. So we have some spikes there. In October, you notice that the spikes aren't as high, and there's more correlation between the points, right? And we see that again along the Front Range. We see the higher values, but things are smoothed out actually in both graphs. But you can notice more continuity here in the October date, and the values actually are smaller on the western slope, and you can see that there's a dip there. But you can actually, this is a view from the other side. So this is looking from Arizona and looking up northeast. And so these are the same graphs, just looking from a different perspective. And this actually should be, I think this should be October. This is the October 3rd date. So was that the 3rd, I think? Yeah, October 3rd. So we talked about the monitoring locations. This is looking at summer versus winter. And what you notice here is what you'd expect, because the ozone problem's worse in the summer. It's worse when the temperature's higher. And you can see in the winter, there's not much going on. And so it's consistent with what we'd expect, that we have higher peaks in summer. In summer compared to winter. Okay, so any questions on that? And this is just looking from the other direction, looking from the southeast towards the northwest. And this is just some information on the parameter estimates. There's actually three, right? We have the fixed intercept, we have the residual variance, and we have the correlation parameter. And you can see how those compare between the different times that I analyze this. So what you do with the spatial temporal model is you join the time points together. And so you'd have a correlation not only between points in space, but correlation over time. And you put it into one model. So one thing you can do if you're doing a spatial temporal model is, to start with, you can do like what I did here. I did spatial models and I stratified it by time, and just to get an initial look at the data. Or you could do longitudinal models stratified by space, although then with 2 dimensions, that's, stratification is a little more complicated. So I think it's maybe easier to think of spatial data at multiple time points, and you can look at each time point and see the changes, and then as a starting point, and then join those together into one spatial temporal model, and you can make graphs and see the progression, or even have like a video to show the changes that are occurring over time. And you guys are probably already familiar with this. Like if you watch the weather, they do that. They show a map, maybe a contour map or something, and they show the progression over time of how the weather's going to change, how the temperature is going to change, or precipitation. So you've seen some output of spatial temporal models probably when you watch weather on the news. Any questions on this? Just some notes of software that you can look into. But I use ProcMix to do this analysis. Is the cool thing, is that I'm using a procedure that we're already familiar with, and I'm showing you kriging just using ProcMix here. I'm going to actually jump to another supplement that I made, because I want to look at this formula just a little bit more closely to show you just intuitively what's going on with this equation. So the Bloop estimators of the missing y, we can break that down into 2 pieces. We have this very intuitive piece, which is our x beta hat, right? That's our population mean piece. And then we have this other piece that's a little more complicated. It's a little bit, probably a little bit more unclear what's going on there until we look at it more closely. So what I did in this, I'll probably not walk through this whole thing, but we can think of this piece here, if just to start with, if we think of the R matrix, the simplest form of that, which is sigma squared I, right? Then you can think of the piece in brackets here as standardized residuals, where you just take the observed y, you subtract off predicted mean values from that, and divide by sigma squared hat. So these are essentially like standardized residuals, and that's gonna be more weighted, so that we can think of this as a localized data piece, and you're going to incorporate that more into your estimate if this correlation between the missing and observed is higher. However, if there's very weak correlation between missing and observed, then the overall mean is going to be weighted higher. So, you know, going back to the data that we have, we saw, you know, and in fact, if I just keep it here, that correlation between missing and observed is higher on the right side, and it's lower here, right? Because as you move away from those monitors, you quickly go back to the population mean. So we see a case on the left side where that correlation is much smaller there and then much higher on the fall date. Okay, so I just wanted to show you that. The other thing I want to talk about in the spatial slides that's the full, that's the one, not the one I want to do. So this one, getting back to this one. Semi-variograms. These are things that help show you how the correlation behaves in space. And are any of you familiar with this, or have you looked at this before? A semi-variogram? So the main purpose of it is to try to understand what model structure we should use for the spatial component, or it actually could be used for longitudinal as well. And in particular, if we create a empirical semi-variogram, that'll give us an idea of whether to use like the spatial power structure or spatial Gaussian structure for the correlation, either for space or time. So this is what the semi-variogram is really just sort of the inverse of the covariance function. And we know for the covariance function that if you take 2 points and they're close together, the covariance is going to be higher, right? And then as you spread those points apart, the covariance is going to get weaker and weaker. And the semi-variogram is just flipped from that. As you spread the points out in time or space, that function's going to actually going to get higher and higher. Whereas when they're close, it's going to be smaller. So it's just inverted. Let me just make a note of that real quick. Oh, come on. Maybe if I go down lower here, let's see. And somehow this doesn't, let's see. Okay, I can write up here. So the semi-variogram has an inverse relationship with the covariance function. Okay, so we see some different types here. The exponential or power, so that's essentially like the AR1, right? And if you think of this as inverted, you can see that the correlation drops off quickly and then tapers, right? So that's like the AR1. And again, if you inverted this, if you flipped it around, that's what you'd see for the covariance function. Now the Gaussian, you see it's sort of flat first and then it falls off quickly and then it flattens out again. Does that make sense? Well, it does, because if you think of the CDF, the cumulative distribution function for the Gaussian, it would have that shape, right? We'd have So for a standard normal, you have this shape, right? So this is the PDF for a normal. The CDF, you don't have much area in the tail, so you're accumulating little, and then you're going to accumulate a lot in the middle. So it's going to be like this, and then it's going to flatten out. So that's a CDF of a normal. And so that's why I think this shape should make sense for the Gaussian. The linear says that there's just a linear change as you increase distance between points. What do you think about that one? Does that work well? What's one of the problems that you have with that one? Well, this line keeps going straight and it'll keep going up. So the problem is you need to truncate that, right? And if you think of the covariance, if you flip that around, you know, if you have this kind of situation where you have a drop in the correlation as time is spread out or space is spread out, that's going to keep going down and then go below zero, right? So you obviously have to truncate that if you're looking at the covariance function. And so it's a similar thing if you're talking about the semi-variogram, where it's going up. There should be a point where there's a point where it has to stop, so you have to truncate it somewhere. So that's one of the downsides. And also I think the linear is just not as, it might work, it might be feasible for some data, but I think it's not as intuitive as like the exponential power of the Gaussian, which have natural asymptotes that they're dealing with. So on these slides, I don't have the actual semi-variogram, but I think you're probably wondering what exactly is this thing. So I have another slide set that's more full that I'm going to post on Canvas as well. And the semi-variogram this is how it's actually technically defined. For 2 points in space, if we're considering spatial data, it's 1/2 times the variance of your outcome measured at point S1 minus the outcome measured at point S2. So that's the actual definition of the semi-variogram. And if you can assume that the process is stationary and isotropic, what does that mean? What does isotropic mean? That means it doesn't matter, the direction and the orientation of these 2 points doesn't matter, it's the same. And we know stationary means that, you know, the variance is essentially constant over time, or in this case over space, whatever space direction you're going, that we can simplify points S1 and S2 to just some amount h that differentiates the distance between those points. So having stationarity and isotropic properties will allow us to simplify this into a function that just tells us how far apart are they. So if we can make those assumptions, we can write it that way. The empirical version then is just taking the squared distances between the points, adding them up, dividing by the number of pairs we're looking at. So that's the sample semi-variogram. And I think jumping back then to the data, this is just an example for FEV1 as the outcome, and looking at, so for children in the school year 2003-2004, the sample semi-variogram is in black, And the modeled version is using the spatial power function. So interestingly, for these data, it almost looks like the linear might work better, right? I don't know if it yields a better fit, but it seems like we're not capturing it perfectly using the spatial power function, which is the first one I would try. That's the most intuitive, I think. So we can use the semi-variogram. In a nutshell, we can use this to the empirical version of it to see what the best structure is for correlation, either over time or over space. One other thing that I wanted to mention to you as well, if you're wondering, like if you have a data set where you have a number of time points and you're just wondering what structure is going to work, what we've learned so far is you can take some candidates and you can compare them using the AIC, right? But one other thing you can do, if you have a fixed number of time points, you can get a sample covariance structure, and you can even do it like with proc-core. And so if you have the same number of time points for each subject, let's say five to 7 time points, and they're the same, you can actually get a sample covariance structure that doesn't make any assumptions. I guess in that respect, it's kind of like the unstructured. But you can just produce that and then get an idea based on looking at that, what structure might work for you. Some of you may have done that already. So you guys have been quiet. It's time for questions or, because I've been talking, I know, but time for questions or discussion here. So this is kind of a crash course in spatial statistics, and we're doing it using a really easy starting point by considering what we can get out of mixed models, to model spatial data, which is a lot. Now, you can take one step up from this. We've done. Sorry, jumping around. Get back to the spatial. We can get slightly more complicated by, instead of just using a fixed intercept, we can use, if we have data on other predictors, we can incorporate that. I've done probably the simplest type of kriging, where we just have a fixed intercept, but you could add more fixed effects to the model. And you can even add more random effects as well to have a more advanced type of spatial modeling here. Questions?
Can you give a couple more examples of like studies or hypotheses in which you would use these? Like when we went over the ozone data, it seemed like it would be more practical to use fixed effects for like population or humidity or something. Because like, isn't the chemicals in the area more of a function of like the manufacturing rather than like the latitude and longitude?
That's a great idea. You could add as predictors to the model other meteorological variables: humidity, temperature, pressure, wind. But I think it always comes back to this, and this I'm always talking to my clients about this: is what question do you want to have answered? Do you want to figure out the ozone, mean ozone, controlling for other predictors, or do you want to just, what we've done here is we've just estimated ozone levels, almost more descriptively, but by using the spatial methods, we're basically interpolating what the values would be at other locations. Now, we can't really do a good job of it in like Southeast Colorado because there really weren't any monitors down there. So it defaults right back to the overall average. But should you add other predictors? Well, it starts with the question you want to ask. Do you want to figure out, do you want to say, well, controlling for temperature, what is our estimate of mean ozone, or do you want to just estimate mean ozone? So I think it goes back to the main question, or questions that you have. But I will show you, let me show you a couple other, I'm going to show you one other data set, and give me just a second to pull this up. But this was I've had like 3 or 4 people do projects in spatial and spatial temporal modeling. One student did a project on real estate, costs of homes over time, right? And this is in the Denver area, so there's a spatial element was where it was in the Front Range, and then what happened over time. So that was probably 2 or 3 years ago. And then last year, I had a student do a project on bee counts over the nation and how that changed over time. And this is Karen, and she mentioned that she'd allow me to present her work. So let me, give me just a second to pull this up. Projects. I'll get her paper. So, so this is Karen's paper from last year, and she did, so she's looking at bee counts, and so the size of the circle is going to represent percent in decline. So you can see that, you know, in certain regions you have a bigger issue of declining population of bees, and this has been a big issue is for certain species of bees, there's been a decline, and what are the causes of it, and so forth. And so she's looking at this over time, and her temporal component looks like a fairly short time frame that she's considering. Time in days, 0 up to, you know, roughly about a 6-month period. And she also used semi-variogram information to understand the correlation structure that she should use. And she was using our package. So she was able to use GLMM PQL, so pseudo likelihood type of model, and able to use define the correlation structure here in this code. So if you're interested in this, I can provide you with this paper. I think Laurel, you might be interested in this for the work that you're doing now. But again, the key thing is we're trying to account for correlation in space and in time. Now, obviously, if you have the same if you have common time points and you only had one dimension in space, is there a way we could do this in mixed, product mixed or mixed models easily? Anything off the top of your head? Are you guys still seeing my? were you seeing this paper? Okay, I just want to make sure because I don't see the green outline here. Elise, yeah.
I was just wondering if you could use regular spatial power, like instead of using 2 dimensions, just specify 1.
Yeah, you could do that if you just had 1 dimension in space. But what about if you had, 1 dimension for space, like you're essentially a line, okay, in the simplest case. Let's say we're looking at Fort Collins, Denver, Colorado Springs, Pueblo, like a line going up and down Colorado, right? But we also have time. We have 2 dimensions. Do you guys have any thoughts on how you could do that in a mixed model? Let's say we have 5 years and we have each of these cities.
Kroneker's product, maybe?
Yes. You could do a Kronecker product of time versus space. In this case, space is just in 1 dimension. And you could try the Kronecker product if you have the same time points for each of the cities. That would be my first thought as well. But so the issue when we get to spatial data is we go from not just 2 dimensions. We've learned how to do that, right? Accounting for 2 factors. So 2 dimensions essentially. Now we have 3 at least. And that's the issue that we have for spatial temporal modeling, is that we have an extra dimension that we have to deal with. Other questions or thoughts? Does anybody else have project data that deals with spatial data? Wei Xuan, can you tell us again what data you have, what you're working with?
Oh, the data is actually the COVID-19 data by country, and then this should be the daily data, but I actually just make it to be the monthly COVID death and new cases data. So I guess it will be helpful to use the spatial temporal method.
Okay, thanks. So where did you get your data again?
It's called the One World data, I guess.
That's open source. You were able to.
It is the open source, and it is updated daily.
That's interesting. Who is the? Is it like a nonprofit organization that creates that, or is it a something? Do you know who?
Yeah, I guess it's a nonprofit organization because what they're doing is actually using multiple sources to combine all of those data together to obtain the bigger data set, so that the data set contains not only the number of new cases, but also contains some of the healthcare informations by country and stuff like that.
Okay, thanks. Anybody else have spatial data or multi-dimensional data that you're working on? So if not, so we have a couple people that are going to do that, so we can look forward to their talks. Any other questions or discussion that you guys want to have?
I have a question. Should I go first? I'm really unfamiliar with this stuff, but if you don't have latitude and longitude, how much would like projections, like choice of projections, change your estimates if you're trying to get distance?
So tell me what, like, give me an example of what you do have.
Well, it seems straightforward if you have latitude and longitude, but let's say you have a map of something and you have to assign a location to things. Projection, like what map projection you use, I would think would really matter, but I don't know if that's even common with this kind of data.
Yeah, I mean, I think my guess is that you could do a pretty good job even if you don't have latitude and longitude, if you have some other surrogate for the point in space and distance between them. You could probably come up with some pretty good approximations, if you're talking about spatial data, and probably something that would account for the correlation, unless you're doing rocket science or something, right? I think it would probably work to use some surrogate instead, because again, we're mainly interested in accounting for the correlation so that we can. We're most of the time we're still going to be most interested in the fixed effects and doing inference for the fixed effects. Now, in some cases, the correlation itself is interesting. You know, like I showed you with Karen's paper, it's interesting to know, you know, how correlated the problem is for declining bees, like in Texas and Oklahoma, you know, and Arkansas and those areas. Like, where is this? How generalized is this problem in localized regions? So that you can, you know, understand the scope of the problem in that area. And by taking into account the correlation, we're also getting an understanding of how much area it's affecting in certain regions. So now I'm kind of going off on a tangent, but I think to answer your questions, my guess is for a lot of data sets, I think it would be adequate, you know, to find a surrogate rather than just latitude, longitude. Elise, did you have a question or thought?
Yeah, so the ozone data you have from the EPA, actually for my thesis I'm using that kind of data as well as for NO2 from the EPA. And one of the like big problems we're having is that sites would be down for certain amounts of time. So like maybe I have 5 sites in an area in a particular week, but in another week I might have like 2 sites of data because they're all like systematically down. And I'm just wondering, like in a spatial context, like how much like inconsistent missingness might cause issues in your estimations.
Yeah, I mean, it's like one thing we learned with missing data is that if the monitors are down because or if it's tied to the levels of pollution, that's the biggest problem. You know, if they're just down randomly for a couple of weeks for separate reasons, I think it would be less of an issue. But if it's tied, if it's somehow tied to the outcome you're trying to measure, that would be the biggest issue that I could see. And I also think that if you have some information from the site, that's much better than nothing. Like for the data I presented, we didn't have anything in the Southeast, not even partial data. And so that becomes very difficult. But having some data is good. And I think that by doing the spatial temporal modeling, you can estimate better what those sites would have been if you can get an understanding of how things are changing over time. You know, hopefully, you know, the interpolation that you're doing would be more reasonable. But, you know, again, more data better, you know, including partial data is helpful. But again, the biggest thing is, you know, hopefully that the missing data is random, truly random, rather than, you know, random due to what the outcome is, or missing because of what the outcome is.
Real quick, I'm curious if you know, if the kriging method is what like Karen used in R, or if that's like standard in R, or if it's other methods that are used underneath the packages.
I think it's related. My understanding is that it's like kriging, and I think so. She used the reason why she didn't use a mixed procedure is because she has counts, so she wanted to do some type of count model, and that's why she's using pseudo likelihood. That's Caitlin. That's a good question, and I'll double check. But I feel like this is a type of kriging where you're using the points that you have to basically interpolate. But let me double check on that. I'll read this again more thoroughly to see, and get back to you if it's a little bit different than that. Okay, so that puts us out of time. So Wednesday we'll talk about measurement error models and causal inference. So it's kind of like more miscellaneous advanced topics. And then look forward to listening to what you have to say next week and the following week. And when you have time, I'd encourage you to look at the extra homework, although I'm not collecting it. Take a look at that, and then we can also talk about it during the review as well, or office hours. So have a good day, and let me know if anybody wants to talk. I've been getting some emails from students and so forth, and I think I'm talking Wednesday with, was it Emily or Samantha? I'm talking to somebody on Wednesday.
I think both.
Both, okay. Sounds good. All right, have a good day, everybody, and talk to you on Wednesday. Okay, bye.
Bye.